Electron Configurations 3. How to determine and write the valence configuration of an element. We have already learned how to write the full configuration of an element and how to write the noble gas configuration as a shorter way of representing the configuration. In this video, we will learn what the valence configuration is, why it is important, and how to determine what the valence configuration of an element is. The valence configuration is defined this way: the configuration in the valence shell. That is not extremely helpful, because we do not yet know what the valence shell is. Here's the definition: the highest energy shell that has electrons present in the ground state. So the valence configuration is the arrangement of the electrons in the highest occupied shell in the ground state. Remember that the shells are identified by their value of the quantum number n, with the higher energy and greater size going with higher values of n. So the highest energy shell has the highest value of n. Pause the video here if you need time to write down the definitions. The valence shell has the electrons that are typically the highest energy electrons in the atom. These electrons are also the ones furthest away from the nucleus. For both of these reasons, these electrons are the ones that are most likely to be involved in chemical bonding. When two atoms come together, the parts of the atom that make contact are the electrons. It is the electrons that are furthest away from the nucleus that are the ones that make contact. The valence configuration is important because knowing the arrangement of electrons in the valence shell can help us, 1. Understand why elements form the compounds they do, and 2. Predict the chemical properties of an element. The first thing to do is to be able to identify what the valence shell is. In the previous videos, we looked at the configurations of a number of elements. We found nitrogen, iron, and polonium. But how do we know what the highest energy shell is? Remember that the number part of the subshell symbol, the 1 in 1s, for example, or the 3 in 3D, tells us which shell the subshell belongs to. That is, it is the value of n. The valence shell is named by the number value of n. So all we need to do to identify the valence shell is to find the largest value of n in the ground state configuration. For nitrogen, the largest value of n is 2. As you might expect, in this case, the last subshell filled has the highest value of n. For iron, it is 4. That is not the last subshell filled. For polonium, it is 6. And the subshells that belong to the valence shell are split. Let's pause for a moment and make note of a couple of things that relate to the filling order. First of all, each of the groups in the filling order corresponds to one of the rows of the periodic table. Row 1, row 2, row 3, row 4, row 5, row 6, and row 7. Note that each row group, except for row 1, begins with the S subshell and ends with the P subshell that have the number of the row. For example, row 4 begins with 4S and ends with 4P, with 3D in the middle, and row 6 begins with 6S and ends with 6P, with 4F and 5D in the middle. The second point is that the D subshells and the F subshells always appear after an S subshell with a higher value of N. So they never are part of the valence shell. Let's go back to the configurations. For nitrogen, the configuration is 1s2, 2s2, 2p3. So the valence shell is shell 2. And the valence configuration is 2s2, 2p3. For iron, the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So the valence shell is shell 4, and the valence configuration is 4s2. Please note that the 3d, even though it's written after the 4s in the configuration, is not part of the valence configuration because the 3d subshell is not part of the valence shell. For polonium, the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p4. So the valence shell is shell 6, and the valence configuration is 6s2, 6p4. Both of the parts of the configuration that are in the valence shell are written here. It is even easier if we have done the noble gas configuration, because we know that only lower numbers are in the parts of the configuration represented by the noble gas, in this case Xe. So we need only look at the written parts of the configuration to find that the valence shell is shell 6, and the valence configuration is 6s2, 6p4. Although it is possible to find the valence configuration without having either the full configuration or the noble gas configuration, at this point, most of you will need one or the other in order to figure out the valence configuration. Those of you who think they understand this well might want to think about how you would figure out the valence configuration without going through all the work of doing the full or noble gas configuration.